This question belongs to computer organization architecture from the topic modes of transfer, and this was asked in GATE 1987. So the question states, in a microprocessor based system, if a burst TMA request and an interrupt request arrive simultaneously, then the microprocessor attends first to the burst request whether it's true or false. So what's a DMA request? DMA request is basically a direct memory access request which is used to access the memory of the system. And what is an interrupt request? An interrupt request is used when a hardware device wants to send an hardware signal so that it can make the processor stop doing the current instruction and then execute a particular instruction which has been done using the interrupt handler. So let us suppose an instruction I1 is going on. So in our CPU, it will have various phases, like it can have instruction fetch stage, it can have instruction decode stage, it can have execute stage, it can have memory access stage, it can have write back stages. So what happens is that, like, whenever after finishing each stage, the CPU will always look for the DMA request after every phase. But the interrupt request is only seen after the entire instruction has been executed. Like the interrupt request will be checked over here, and the DMA request will be checked after each of the phases. So the answer comes out like whenever we are getting a DMA request as well as interrupt request arrive simultaneously, then the processor will first attend the bus request or the DMA request. So the answer is true. The reason for seeing the interrupt request at the end is that if we allow the interrupt request to be seen in between the phases, then it may change the registers and it may cause some error during the execution of the instructions. This question belongs to computer organization and architecture and from the topic I/O handling, and it has been asked in the year GATE 1987. So the question states that data transfer between a microprocessor, which is basically a CPU only, and an I/O device is usually faster in memory mapped I/O scheme than in I/O mapped I/O scheme. So suppose whenever our CPU or the microprocessor wants to communicate with the I/O device or with the memory, then there are basically three schemes, but the question states about these two schemes only. First one we can say it to be isolated I/O or I/O mapped I/O scheme, and the second one is memory mapped I/O scheme. So as we know that all the communication happens through address bus, data bus, and the control bus. So in the isolated I/O scheme, what happens is that we will have a common address bus for both memory as well as the I/O devices, and the control signals would be separate for both. So like suppose CPU wants to read something from memory, so it will give the address in the address bus, and it will then set these control lines to be true and these to be false so that it can read from the memory. And if it wants to read or write into the I/O devices, then it will set these bits to be 1 and these control signals to be 0. So here, as we can use the entire memory space, so we can say that the isolated I/O or I/O mapped I/O or port mapped I/O has different address spaces for both I/O devices as well as the memory. Now let us consider this memory mapped I/O scheme. In this I/O scheme, we will have a common address bus, data bus, and control bus for both this memory as well as the I/O devices. So here, what we will do is that we will have to divide the memory into two parts as we are using the same address, data and control bus. So we need to make a distinction between the memory and I/O. So we will have different address spaces for memory as well as for the I/O devices. So the question stated that different data transfer between a microprocessor and I/O device is usually faster in memory mapped I/O scheme than in I/O mapped I/O scheme. As we can see in I/O mapped I/O scheme, we have this separate logic for this I/O control lines. So it will be generally slower. And in memory mapped scheme, there is distinction between the various parts of memory, so it is generally faster as it do not have any logic of these control lines. So it's true as the memory mapped I/O scheme is faster than the isolated I/O scheme. This question belongs to data structures and algorithms subject, and the topic is binary tree. So the question states that is it possible to construct a binary tree uniquely using pre-order as well as post-order traversals? So A binary tree can be constructed uniquely only by these three possible orders. You can remember these orders. In order is necessary always, and it can be mapped with either pre-order, post-order, or level order. And it can't be constructed by any other possible pairing. Like we can't construct it using a pre-order, post-order, pre-order, level order, or post-order, level order. As unique, the unique term is most important here. Uniquely, it can be constructed by these three, and it can't be constructed uniquely by these three. I will give you an example. Let us suppose we have a binary tree 1, 2, and 3. So, what will be its pre-order? So, its pre-order would be first node, then left subtree, then right subtree. So, it would be 1, 2, 3. What will be its post order? Its post order will be first left subtree, then right subtree, and then node. So it would be 3, 2, followed by 1. Now let me take another tree. Another tree is like this: 1, 2 as its left child, and 3 as its right child. So what will be its pre-order? Its pre-order would be node followed by left subtree followed by right subtree. So it will be 1, 2, and 3. And what will be its post order? Its post order will be left subtree followed by right subtree followed by node. So it would be 3, 2, and 1. So here you can clearly observe that if we were given this pre-order and post-order, pre-order is 1, 2, 3, and post-order is 3 to 1, then we can construct two binary trees with this. Like we can have 1, 2, and 3, this Q tree, and we can have another tree like this. So we can't construct a unique binary tree. We can construct a binary tree, but unique one we can't construct. So unique binary tree can't be constructed using pre-order and post-order traversal. So the answer is false. This question belongs to engineering mathematics subject and the topic is sets and relation. It was asked in GATE 1987. So the question states that the union of two equivalence relation is also an equivalence relation, state whether it's true or false. So we know that an equivalence relation is a relation which is reflexive, symmetric, as well as transitive. All three properties must hold. So these are some basic equations. The union of two reflexive relation is always a reflexive relation. The union of two symmetric relation is always a symmetric relation. But the union of two transitive relation, it can either be a transitive, it may be a transitive relation, or it may not be a transitive relation. So as equivalence relation is combination of reflexive, symmetric, and transitive, we can say that the union of two equivalence relation may or may not be another equivalence relation. It happened because the union of two transitive relation may or may not be transitive. Let me give you guys an example for this. Let us suppose we have a set which has defined over A, B, and C. Now we have two relations R1 and R2 defined over this set A. So this R1 has AA, BB, and CC. As it has all AA, BB, and CC, so it's reflexive. Then it has AB and BA. As it has AB as well as BA, so it's symmetric. And it's transitive also, as there are no condition violating the transitive property. So it's an equivalence relation. Now consider another relation R2. It has AA, BB, and CC. Thus it is reflexive. It has CB and BC. Thus it is symmetric, as there is no condition violating the transitive property. Thus it's transitive also, and hence it is another equivalence relation. Now let's combine both these relations to form R1 union R2. So it will have AA, BB, CC, AB, BA, CB, and BC. Now let us see whether this R1 union R2 is an equivalence relation or not. It has AA as well as BB as well as CC, thus it's reflexive. It has AB and BA, thus it's symmetric. It has CB and BC, thus it's transitive. But now let us see whether an transitive property is violated or not. Like it has AB, it has BC, but it do not have AC. So AC is not present over here. In this relation, AC is not there. Thus, it's violating the transitive property. Thus, the union of two equivalence relation may or may not be an equivalence relation, and hence this is false. It can be an equivalence relation or it may not be. And it's asking like in every condition it will be an equivalence relation or not. This question belongs to data structures and algorithms. Okay, and the topic name is graphs, and It was asked in K 1987. So the question states that whether there exists a linear time algorithm for testing the planarity of finite graph. So we will be given a finite graph and we have to check whether it's planar or not and whether we can find whether it's planar or not using a linear time algorithm. So it's a true false based question. So we can do this by using modified depth first traversal which takes order of v plus e times. So order of v plus e means it's a linear time algorithm. And there is another algorithm available for it by Hopcroft and Target. They have proposed an algorithm in their paper, Efficient Planarity Testing. I have given the link for the paper. Guys who want can refer it. And it can check whether a given graph is planar or not using order of n time algorithm, which is linear time algorithm. So by using either of them, we can check whether a given graph is planar or not. So there exists a linear time algorithm. So the answer is true. This question belongs to engineering mathematics subject and the topic is sets and relation. So the question states that every infinite cyclic group is isomorphic to the infinite cyclic group of integers under addition. We have to tell whether it's true or false. So the definition of infinite cyclic group states that let us suppose we have a group G, then it can be represented as G equals to A, where as it is a cyclic group, so it means that for all the integers k belonging to z, it will have all powers of k, like it will have a power 0, a power 1, a square. So this is infinite cyclic group, and even for the negative integers. Now let us define a mapping phi. So this phi will be from integers to this group G, and we can define phi of k as a to the power k. Now, as given in question, we have to prove that phi is an isomorphism. So first of all, we will use a p-proved statement that we have proved over here. It states that from a mapping from additive group of integers to the powers of group, element is homomorphism, then phi is a homomorphism. I will tell you the proof of this later on. Now, for the second one, assume that we have to show that phi is a surjection. So how we can show that? As we know that G is a cyclic group, it has been written over here, then every element of G is a power of A, as we have proved over here, for some A belonging to G. So if an element A belonging to G, then we can write that element as, let us suppose we have some element X belonging to G. Then there must exist some K whose raised to the power equals to X. As it is a cyclic group and X is an element of the group, then there must be some integer K whose when A is raised to the power K, we will get X. And by the definition that we have defined over here, we can say that phi equals to phi of k. And if it is a phi of k, then we can write it to be a to the power k. And we know a to the power k equals to x. Thus, phi is a surjection. Now we have to prove that phi is an injection, like it is 1, 1. So how we will do is that, like suppose we have m and n belonging to the integers, and then let us suppose m is not equal to n. Then we already know that if m is not equal to n, then a to the power m won't be equal to a to the power n. Like we have 2 and 3, then a square is not equal to a cube. So thus it is an injection. Phi is an injection. As we have proved that phi is an injection, we have proved that phi is a surjection and phi is a homomorphism. We have proved over here. I will show you the proof. Thus phi is an injective surjective homomorphism. Thus, we can say that every infinite cyclic group which is G is isomorphic to the infinite cyclic group of integers under addition, which is what we have to prove. So this is true. Now I will show you the proof of this one, like uh, from mapping from additive group of integers to powers of group, element is homomorphism, then phi is a homomorphism. Let us suppose that we have a group G0, then an element G belongs to the group. Then we can denote z comma plus with the additive group of integers. This is basically the theorem and this is the proof for it. Then we can define phi of g to be from z positive to the group. We are mapping defined as, like for all the integers we can write phi of g of k to be g to the power k. It's a mapping which has been defined for z plus to the g 0. Then we have to prove that phi of g is a homomorphism. So how we will prove that? Suppose we have two elements k and l belonging to integers. By this definition, we can say that as k and l belonging to, then we can write that phi of g of k plus l. What will be? It will be, according to the definition, it should be g to the power k. Here g is g and k is k plus l. So it will be equal to g to the power k plus l. And we can write it as g to the power k into g to the power l. And we can also write it as phi of g of k into phi of g of l. Thus, we can easily say that it is also a homomorphism. Thus, it is a surjective homomorphism and an injection. Thus, every infinite cyclic group is isomorphic to the infinite cyclic group of integers under addition. This question belongs to data structures and algorithms and comes from the topic binary tree and was asked in GATE 1987. So the question states that if the number of leaves in a tree is not a power of 2, then the tree is not a binary tree. So let me tell you the definition of binary tree. So the definition of binary tree states that each node can have at most two childs. At most two childs. So let us break down this at most two. At most two means it can have 0 child, it can have 1 child, it can have 2 child. So let us suppose we have a tree like this. So this node has 0 child. Is it a binary tree? Yes, it is a binary tree. Let us consider this. It has 1 child, this one has 1 child, this one has 0 child. Is it a binary tree? Yes, it is a binary tree. Now whether this is a binary tree, this has 2 childs, this has 0 childs, this has 0 child. Yes, it is a binary tree. Now let us consider this one. Whether it is a binary tree or not. Yes, node 1 has 2 childs, node 2 has 2 childs, node 3 has 0 child, node 4 has 0 child, node 5 has 0 child. So everyone has either 0, 1 or 2 childs. Thus it is a valid binary tree. Now let us count the number of leaf nodes. Leaf nodes are the nodes which have 0 child. So here we have 3 leaf nodes. We have 3 leaf nodes. And whether 3 is a power of 2 or not, no, it is not a power of 2. Thus we can have the number of leaf nodes which are not a power of 2 and still the tree can be a binary tree. So if the number of leaves in a tree is not a power of 2, yes, 3 is not a power of 2, then the tree is not a binary tree. False, as this is a binary tree. Thus the answer is false. This question belongs to theory of computation and the topic name is regular language and it was asked in GATE 1987. So the question states regularity is preserved under the operation of string reversal, whether it's true or false. So what this question is asking is that we are given a language which is given to be regular language, and if the reverse of and the string which this language represents, if we do the reverse of that language, whether it will be regular or not, whether L reverse is regular or not. So we know that a language is regular if we can draw a DFA for it or an NFA for it, or we can write a regular expression for it. If you need a shortcut, then regularity is preserved under union, intersection, clean closure or star closure, concatenation, complementation, difference, as well as reversal. So according to the shortcut, regularity is preserved under reversal. And it's not preserved under subset operation and superset operation. Now, let me tell you the logic, like how can we prove that it is preserved under this operation? So if a language is regular, let us suppose L equals to AB star, it is a regular language. How can we know that it is a regular language? If we can draw DFA, NFA or regular expression for it. So AB star is a regular expression and this is the NFA for this. As we can draw NFA for AB star, thus it is a regular language. How then what will be the reverse of AB star? AB star reverse will be BA star, as AB star reverse will be BA, B star A. Thus, we can draw up the reversal NFA by making the initial state as the final state, making the final state as the initial state, and by reversing all the arrows. Like A was going from left to right, initial to final, now it is going from right to left, and B remains the same. So as we can draw another NFA for the reverse of the language, thus the regularity is preserved under the string reversal operation. Thus the answer is true. This question belongs to theory of computation and the topic name is regular language. It was asked in GATE 1987. So the question is true false based question which asked whether all subsets of regular sets are regular. So what is a regular set? Regular set is a set which is represented by a regular language. So what is a regular language? L is regular if we can draw a finite automata which is either a deterministic finite automata or a non-deterministic finite automata for it, or we can write a regular expression for it. So it is a shortcut like the regularity for is preserved under union, intersection, star closure or clean closure, concatenation, complementation, difference, and reversal. And it's not preserved under subset and superset. So the question asked whether all subsets of regular sets are regular or not. So as it is not preserved under subset, so all subsets of regular set are not regular. It may be regular or it may not be regular. Now let me give you an example. We have a language L equals to A star B star. Now let us consider a subset of this language L dash. We can consider it to be AN, BN. We know this language is not regular as we need to keep a track of number of A's and number of B's. So we need a memory for it. So we cannot draw a finite state machine for it. So it's not regular. So L dash being a subset of a regular language may not be regular as it is not regular. Thus this is false. You can also remember some key points like every finite subset of a regular or a non-regular language is always regular. This question belongs to theory of computational subset and the topic name is finite automata. It was asked in GATE 1987. So the question states that a minimal DFA that is equivalent to an given non-deterministic finite automata or an NFA has always 2 to the power n states. So like suppose NFA has n state, then it is asking whether when we convert the equivalent minimal DFA for the given NFA, it will always have 2 to the power n states or not. So it's a true false based question. So it's a standard theorem that for a given NFA with n states or a NDFA with n states, the equivalent minimal DFA will have at most 2 to the power n states. Not always at 2 to the power n states, it will have at most 2 to the power n states. Or we can also say that the number of states in a minimal DFA will be greater than 1 and will be less than equal to 2 to the power n. I will give an example for this. Like we haven't given NFA for a language which is given over here. When we convert this to its equivalent minimal DFA, then we will get this corresponding DFA. So here the number of states were 4 and here we have got 3 states. So it's definitely not less equals to 2 to the power n, as it would have been if it would have been 2 to the power n, then it would have been 2 to the power 4, which is 16. But it's not 16, it's 3. So the correct answer is false. It's at most 2 to the power n state, not exactly 2 to the power n state. This question belongs to theory of computational subset and was asked in GATE CSE 1987. The topic name is context-free language. So the question asks whether the intersection of two CFL is also a CFL, if it's true or false. We know CFLs are not closed under intersection, which means the intersection of two context-free language may or may not be a context-free language. So the answer is false. Let me give a contradicting example. Suppose we assume that the intersection of two CFL is always a CFL. Now we can easily contradict this statement. Let L1 be a language given by a to the power n, b to the power n, c to the power m, where n and m is greater than equal to 1. As here we need to compare just whether a and b are equal or not. Thus, it can be done using one stack and is a context-free language. Let us consider another language L2, which is defined as a to the power n, b to the power m, c to the power m, for n and m greater than equal to 1, as we have to compare just whether the number of b's and number of c's are equal or not, which can be done using one stack. Thus, this is also a CFL. Thus, L1 is a CFL and L2 is also a CFL. Now let us find the intersection of two languages, L1 and L2, which is equal to a to the power n, b to the power m, c to the power m, for all m is greater than equal to 1. As here we need to compare whether the number of a's and number of b's are equal and whether the number of b's and number of c's are equal. Thus, it has more than one comparison. It has two comparisons. Thus, it cannot be done by using one stack or by using a context-free language. It's basically a context-sensitive language. Thus, we have arrived at a contradiction that the intersection of two CFL is not a CFL. Thus, CFLs are not closed under intersection, and the intersection of two CFL may or may not be a CFL. Thus, the answer is false. This question belongs to theory of computational subset from the topic Turing machines and was asked in GATE 1987. So the question states, if A is recursive, if both A and its complement are accepted by Turing machines, whether it's true or false. We can rewrite the given statement as, if A and A complement are accepted by Turing machine, then A is recursive or not. So let us suppose we have a language A which is recursively enumerable, which means there exists a Turing machine TM1 such that given any string of the language A, the TM1 will halt and accept the string. Now let us also suppose that the complement of A, which is A complement, is recursively enumerable, which means that there is some other Turing machine TM2. Given any string of A dash, TM2 will halt and accept the string. So any string either belongs to A or A complement. Hence, any string will cause either TM1 or TM2 to halt. Thus, we can construct a new Turing machine, TM, which emulates both T1 and T2 and alternatively moves between them. When either one of the stops, we can tell to which language the string belongs. Thus, we have constructed a Turing machine, TM, which has both TM1 and union TM2. For each input, it will halt with an answer whether or not the string belongs to A complement or not. Therefore, A and A complement are recursive languages if A is recursive. This question belonged to Digital Logic Design subject and was asked in GATE CSE 1987. It's related to the topic Boolean functions. So the question asks the total number of Boolean functions which can be realized with 4 variables is, and we are given 4 options. So there is a direct formula for this. The number of Boolean functions for n variables equals to 2 to the power 2 to the power n. So here n is 4, where n is number of variables. So 2 to the power 2 to the power 4, which is equal to 2 to the power 16, which is equal to 65,536. So this is a direct formula. So the logic for this is, suppose we have 4 variables. Now we have 4 variables A, B, C and D. So what are the number of combinations we can make out of these 4 variables? As each of them can either be 0 or 1. So the number of possible combinations equals to 2 into 2 into 2 into 2, which is equals to 2 to the power 4, which is equal to 16. We can have 16 combinations. So here are those 16 combinations. And a Boolean function is basically a mapping from these 16 elements to the set 0 or 1, which means some of these function elements may come in the Boolean function, some may not come. So either they can be 0 or 1. So thus we will have 2 to the power 16 Boolean functions, as it is a mapping from 16 elements to the 2 elements. Thus the number of Boolean functions possible equals to 2 to the power 16, which is equals to 65,536. This question belongs to Digital Logic Design subject and was asked in GATE 1987. The question's topic name is sequential circuits. So the question states, the above circuit produces the output sequence. So we are given a circuit. This is a clock, this is a NOT gate, this is an XOR gate, and this is the output. We have used JK flip-flops all over there, and we need to find out what is the sequence that we will get for this output. So we all know the characteristic equation for JK flip-flop is the next state Qn plus 1 equals to J Qn complement plus K complement Qn. So let us try to expand this for our given flip-flop. So we will have J. Let us expand this for this flip-flop. So J will be J only, Qn will be Qn complement only. Now K, what is the K over here? K over here is, we are using a NOT gate over here. So K is J complement. You can write K to be J complement pole complement Qn. If we will expand it, we will get Qn plus 1 equals to J Qn complement plus J, Qn. Now if you will take J as common, then we will get Qn plus Qn complement. We know any variable plus its complement is always 1. It's a standard equation. So we will get the next state Qn plus 1 equals to J. So we know we have already seen an equation like this for the D flip-flop. We know for the D flip-flop also the next state equals to D. For D flip-flop, D will come over here and the next state Qn plus 1 will be equals to D. And same we are coming over here. It's happening because we are using a NOT gate over here. So this JK flip-flop will act like a D flip-flop. So now we will try to find out what will be the output for this. So let us analyze the output. So we can easily analyze the output by the shortcut methods. I will tell you those methods. So the equation that we have got is, let us write it over here. It's a D flip-flop. Okay. So now what? Let us name it as Q3, this as Q2, this as Q1, and this as Q0. These Qs I have renamed. So let us assume Q3, Q2, Q1, followed by Q0. Now let us try to find out what will be its value. What is Q3? We know that the equation that we have found out previously was Qn plus 1 equals to J. Okay, and it's acting like a D flip-flop. It's acting like a D flip-flop. Okay, so what will happen is Q3 will be equal to this J. It will be equals to J3. And what's J3 value? J3 is getting its value from here, which means Q1 XOR Q0, which is equals to Q1 XOR Q0. What is the value of Q2? Q2 is getting its value equal to J2. And what's J2? J2 is equals to Q3. So we can write it as Q3. What's the value of Q1? Q1 is value is equals to J1 and J1 is getting its value from Q2. So it's equal to Q2 and Q0. Same goes for Q0. Q0 value equals to J0 and J0 value equals to Q1. So we can easily see that if initially we are having, we can assume any initial value 1, 1, 1, 1. Let us assume it to be 1, 1, 1, 1. So what happens in the next clock pulse? In the next clock pulse, we can easily see that Q2 gets Q3, Q1 gets Q2, Q0 gets Q1, which means these three bits get shifted to the right. So means this bit comes over here, this bit comes over here, and this bit comes over here. So we can easily write it as 111. Shifting these bits. And what happens to this bit? Q3 equals to Q1 XOR Q0, which means both these XOR. So what is 1 XOR 1? 1 XOR 1 is 0. Now let us find for the next clock pulse. These three will shift, so we will get 0, 1, 1 and 1 XOR 1, which means 0 we will get over here. In the next pulse, these three will shift, we will get 0, 0, 1 and 1 XOR 1, which means 0. Now these three will again shift, we will get 0, 0, 0 and 0 XOR 1, 1 they will get over here. Now again there will be a shift 1, 0, 0 and 0 XOR 0, 0 we will get over here. Again there will be a shift of 3 bits and 0 XOR 0, 0 we will get over here. Again there will be a shift of 0, 0, 1 and 1 XOR 0, 1 we will get over here. In the next clock pulse, again let us write it Q3, Q2, Q1, Q0. Again there will be a shift 1, 0, 0 and 0 XOR 1, 1 we will get over here. Again there will be a shift 1, 1, 0, 0 XOR 0 we will get over here. We can carry this forward, but we can easily see what's the answer. So what is the output? Output value equals to Q0 value. So Q0 is the output. Let's find out what is the value. 1, 1, 1, 1. We'll get 1, 1, 1, 1, 0, 0, 0, 1 followed by 0, 0. So what option is matching? If you want, we can even carry it forward like 0, 1, 1, 1 XOR 0 is 1. But no need to carry forward unnecessarily if you know like what's the answer. So 4 ones followed by 3, 0, 1, 0, 0, 1 and it will carry on forward. So the option is option C. 4 ones followed by 0, 0, 1, 0, 0, then 1, 1 will come followed by 0, 1, 0, 1 and it will carry on. The option C is correct. This question belonged to digital logic design from the topic multiplexer and was asked in GATE 1987. So the question states the above circuit produces the following sequence. So we need to find out what is the value of this output F for this given sequence. So what's the standard multiplexer? It's a 4 cross 1 multiplexer with 2 select lines. So if we have a 4 cross 1 multiplexer with 4 inputs A, B, C and D and 2 select lines, let us name it to be B and A, and a output F, then the equation, standard equation is like for these values for B and A, if it is 0 0, it can have 0 1 1 0 as well as 1 1, and the output F will be equals to, for 0 0 F will be equals to A, for 0 0 F will be equals to A, for 0 1 F will be equals to, wait a second, yeah, F. For 0 0 F will be equals to A, for 0 1 it will be equal to B, the second line, for 1 0 it will be equal to C, and for 1 1 it will be equal to D. So let us find out the value of F for this circuit. So F will be equals to, and we can also write F over here to be equals to B complement A complement. 0 means complement, so B complement A complement into A plus B complement A into B plus BA complement into C plus BA into D. So we can write F to be B complement A complement A. What's the value of A over here? It's C, plus B complement A. What's the value of B over here? It's C complement, plus B A complement. What's the value of C over here? It's C complement, plus BA. What's the value of D, which means the last select line? It's C. Now let us try to expand this equation. Okay, so we can, from this term as well as this term, we can take C as common. So we will get C B complement A complement plus BA, and the leftover terms, let us take C complement as common. We will get B complement A plus BA complement. Again, we can write it as, okay, it's an XNOR equation, so we can write it as B XNOR A plus C complement. It's an XOR equation, we can write it as B XOR A. Okay, as we know that XOR and XNOR are commutative, so we can write it as A XNOR B equals to B XNOR A, and same goes for XOR, it is also commutative. Now let us assume this to be a, now we know that if we have two terms, XOR and XNOR are complement of each other, we can write A XNOR B as A XOR B whole complement. So we can write it as A XOR B whole complement. It's a complement. Let me erase this to make sure no confusion arises. It's A XOR XNOR B over here. It's C A XOR B whole complement plus C complement into A XOR B. Now what we can do is that we can assume this term to be X and this term to X complement and this term to be X. So we can rewrite this as F equals to C X complement plus C complement X. Now again it's an XOR equation, AB complement plus B complement A. So we can write it to be C XOR X, which is equals to X XOR C. Now let us put the value of X. So what was X? We have assumed it to be A XOR B. So we can write F equals to A XOR B XOR C. So the correct answer is A XOR B XOR C, which is option B. This question belonged to computer organization subject and was asked in GATE 1987. It is a question which belongs to addressing modes topic. So the question asks the most relevant addressing mode to write position independent codes is direct mode, indirect mode, relative mode, and index mode. Let me explain all the modes. So what happens in direct mode is, like whenever we have an instruction, so instruction will have two parts. First one will be an opcode part and the second one would be an address. it will be a memory address, and when we will go to this address in the main memory, then we will get our operand that we need to perform the operation on. So it needs just one memory access. This is direct addressing mode. Then we have indirect addressing mode. So what happens in indirect addressing mode is that we will have our instruction, we will have our opcode, and then we will have an address. When we go to this address, then we will get another address 2, and using this address we will get the actual place where our operand is present. So in this we need two memory access, first to get the address A2 and the second one to get the fetch the operand from the address A2. Then we have relative mode. What happens in relative addressing mode is that we will have our opcode as well as we will have our address. So what we do is that we will have a program counter. Program counter is basically a register. So we will add the content of the program counter and this address to get the effective address in the main memory where our operand is present. And the fourth one is index mode. So what happens in index mode is that we will have our opcode, we will have a index value, and then we will have our address. So what we will do is that we will go to the register set and find the index register value. We will combine both these addresses and we will get the effective address. Then we can go to main memory and get our operand from the memory. So the question asks like which of these mode is preferred if we want position independent codes. So here it is hard coded, so it's not preferred as we cannot write position independent code. Here also it's hard coded. This address is hard coded, so it's not preferred. Here we will need to provide the index value over here only, so it is also not preferred. Here, if you want to write position independent code in the relative addressing mode, then we can change this program counter value, keeping this offset value as the same. And in that case, we can write the position independent codes. So the correct answer is relative addressing mode. This question belongs to computer organization subject and was asked in GATE 1987. So the topic name is microprogram control unit. So it is asking a microprogram control unit is faster than hardware control unit, facilitates easy implementation of new instruction, is useful when very small programs are to be run, usually refers to the control unit of microprocessor. So basically when we have control unit, so control unit can be implemented either by microprogram method or by hardwired method. I will tell you the difference between both these methods first. So here is a diagram facilitating what a hardwired control unit is and what a microprogram control unit is. So what a hardwired control unit is, we will use the hardware logic. Hardware logic means like we will use the gates, we will use flip-flops, and then it will be hard coded. It will be hard coded as we have, you can see we have we have decoder over here, we have control signal generator. All these are hardware devices, step counter, and we will use some clocks and enables, and then we will generate for a particular instruction. We will have this hard coded structure which will give us the control signals as the output, and we can't change this hardware structure. Like for each instruction we can't change it, it's very static structure. And the second one is microprogram control unit. So what happens in this is that suppose we have an instruction, ins1, then we can assume the instruction to be made up of various types of microprograms, and a microprogram can be assumed to be made up of micro instructions, a micro instruction or a control word. We can assume it to be n bits. We can have n bits control word or n bits micro instruction. As these are 1 0, a sequence of 1 zeros, for all these 1 zeros we can create n control signals by using control ROM. So this logic is written basically in the control ROM, like how we need to generate these control signals by using this control word. Now let us see our options. So the option 1 states microprogram control unit is faster than hardwired control unit. It is false, as in microprogram control unit we have this extra logic of control we have this software logic is built over hardware, hardware. It is microprogram control unit is built over hardware control unit, but it provides a flexibility. So it's basically not faster, it's slower than the hardware control unit. So option A is false. Now let us see option B, facilitates easy implementation of new instruction. And we can see that the logic here is written in control ROM. It's a hardware structure, but we can rewrite the ROM as there are erasable, programmable, read-only memory available. We can rewrite the ROMs by using some electrical signals. Thus, it is possible to facilitate easy implementation of new instructions. Let us see option C. It is useful when small programs are to be run. No, false. Hardware control unit is basically preferred when small programs are to be run. As for small programs, we will have very few set of instructions, and for them writing a hardware control unit is easier than writing a microprogram control unit. So option C is false. Option D states that usually refers to the control unit of microprocessor. As we have seen, control unit can be implemented by hardware method or microprogram method. So both of them, hardware and microprogram control unit, both of them signifies the control unit of processor, not only microprogram control unit. So the answer is option B. This question belongs to digital logic design subject and was asked in GATE 1987. The topic name is number systems. So the question asks, the exponent of a floating number is represented in XSN code so that the dynamic range is large, the precision is high, the smallest number is represented by all zeros, overflow is avoided. So like when we have floating number, then there can be two numbers. Either we can have positive number or we can have negative number. So we are using SEM representation to represent the numbers. It is three fields: sign, exponent, it's a standard format, and mantissa. So what we does is that when we have positive number and we have negative number, so we need to handle this negative number case. So negative number case can be handled by three methods. First one is sign magnitude. Sign magnitude representation of the negative number, we can have ones complement representation or we can have twos complement representation. So basically here twos complement representation is preferred over the ones complement and sign magnitude representation, because in twos complement we have one extra number which can be represented, so its range is basically more than ones complement. So we use 2's complement, but the disadvantage with 2's complement is like, suppose we have a negative number, two negative number, and we want to compare them. Then we first need to convert them to positive number, and then we need to compare. So it's a time-taking process. That's why we are not using this 2's complement method. So what we are using to represent here in the exponent field is the excess encode. So what excess encode states is that we will define a value n, and all the numbers, all the values greater than equal to n will represent positive number, and all the values less than equal to n will represent the negative number. So here we can also, if this n is flexible, so like we can suppose we have a number line, we have n over here, and this is the range. So we can represent negative number over here, we can represent positive number over here. And if we change the n to over here, then the positive number range reduces and negative number increases. And if we move n to the left side, then negative number reduces, range reduces, and positive number increases. So this n is flexible. So what we can do is that if we are using excess n code, then we can represent the smallest number by all zeros. We can represent the smallest number by all zeros. And if you want to find like the smallest number will have all zeros in this exponent field, all will be zeros. And if we need to find the actual number which was present in the exponent, then we just need to do 0 minus n to find the actual number. Now let us see the options. So first option is dynamic range is large. No, dynamic range is large is a false option, as what a dynamic range is. Dynamic range means the range of numbers which can be represented, the absolute range of numbers that can be represented. So the range always remains the same, we are just changing the n. So this option is false. The second option is Precision is high. This is also false as there is no effect of precision, and even like in access encode the precision is slightly less due to scaling. Fourth option is overflow is avoided. No, it's not related to overflow. And the third option is the smallest number is represented by all zeros. Yeah, we have seen in access encode the smallest number can be represented by all zeros, so that it makes the calculation easy. We can directly compare two numbers. So the option C is correct. This question belongs to computer organization subject and the topic name is interrupt. It was asked in GATE CSE 1987. So the question states, on receiving an interrupt from a IO device, the CPU does what of this? Halts for a predetermined time, hands over control of address bus and data bus to the interrupting device, branches off to the interrupt service routine immediately, or it branches off to the interrupt service routine after completion of the current instruction. So what an interrupt is like CPU, there is an instruction that is being executed. Now an IO device which can be your CPU or it can be a mouse or printer or anything wants to do some task or wants to get some service, then it will send an interrupt signal to the CPU, and CPU will then do the necessary action based on this interrupt signal. So it's asking what happens when an interrupt signal comes. So it's a predefined things like what happens when an interrupt comes. Let me tell you all these things. So what happens is that suppose CPU is executing the program. So after completion of the program, after completion of each instruction, not within the instruction, like interrupt may come at any point, but after completion of each instruction, it will check the interrupt pin, whether an interrupt has came or not. Like suppose a interrupt came somewhere in middle and it got caught when the instruction ended. So what happens is that CPU checks the status bit of the interrupt at completion of each current instruction running, whether there is an interrupt, and when there is an interrupt, then it calls the interrupt service routine. So after completion of each instruction, it will check and then it will call an interrupt service routine. So what an interrupt service routine is that? Interrupt service routine is basically a software routine that hardware invokes in response to an interrupt. Interrupt service routine basically examines the interrupt and determines how to handle the interrupt. And what happens during this execution, there are some steps which happen. It's necessary to like remember them. So what happens is that the interrupt handler will determine the cause of the interrupt. It will perform the necessary processing according to this interrupt service routine, and then it will perform a state restore after the processing and will execute a return from interrupt instruction to the return control of the CPU. So the program control returns to the interrupted program over here, and then it will start executing from the next instruction where it was interrupted. So the options are halts for a predetermined time. No, it doesn't halt. Hands over control of address bus and data bus to the interrupting device. No, this is also false. Branch off to the interrupt service routine immediately. No, not immediately. After execution, completion of the current instruction, it will branch off. Branch off to the interrupt service routine after completion of the current instruction. Yes, option D is correct. This question belongs to digital logic design subject and was asked in GATE 1987. The topic name is DRAM, which is dynamic RAM. So the question states the refreshing rate if a dynamic RAM is in the range of 2 microseconds, 2 milliseconds, 50 milliseconds, or 500 milliseconds. So it's basically a question which you need to learn. You need to pre-know it. So first, let me tell you the logic of what is this refreshing rate meaning. So what happens is that we have a RAM, or we can say a DRAM. So what happens is how data is stored. Data is basically stored. Each bit is basically stored as a charge, and it is retained using a capacitor. And as we know, as time passes, this charge on the memory will start leaking, and thus the data which was stored as a charge on the chip we will start losing the data. So we have an external circuit. So what this circuit does is that it basically reads each memory cell, the charge over there, and then rewrites it immediately so that we can retain the charge in the capacitor, so that we will be able to retain the data. So what's the refreshing rate? So if you want to read, you can basically find out a document regarding this. So it's basically a patent which is available on this link. You can basically go to this link, https://patents.google.com. This is the patent number, and the topic name is Dynamic Random Access Memory Refresh Circuit selectively adapted to different clock frequencies. Here you can see in this line it's written, a row of dynamic RAM memory is refreshed during each memory access by the refresh circuit so that during a 2 millisecond interval all the dynamic RAM memory is refreshed. So here it's written 2 millisecond. So the option is 2 milliseconds. Option B is correct. So basically you need to pre-know this value, but the logic I have explained you, the refreshing logic is the same, and you need to pre-know this 2 millisecond value. This question belongs to compiler design subject and was asked in GATE 1987. The topic name is stages of compiler. So the question states, in a compiler the module that checks every character of the source text is called the code generator, the code optimizer, lexical analyzer, or syntax analyzer. So what is a compiler? A compiler is basically a software which takes our high level language and converts it into assembly level language. So there are basically 6 stages of this compiler. This compiler has 6 stages. Let us analyze all these 6 stages. So these are the 6 stages of the compiler. So what it does is that it takes a high level language and gives output as assembly level language or assembly level code. It uses symbol table as well as error handler. Let us focus on these phases. So we have lexical analyzer phase, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and target code generation. So what happens in this lexical analysis phase is that, suppose we have got our C statement. So our C program will have statements like int a equals to 5. So what this lexical analyzer does is that it takes this program line by line and it scans the lexemes. So all these are lexemes. Int a is lexeme, a is lexeme, equals to is lexeme, 5 is lexeme, and this is lexeme. It scans the lexeme and matches the lexemes with the patterns. It matches the lexeme with the patterns to find out the tokens. So what happens is that we basically have finite automata, a DFA or NFA with outputs, and we will match these lexemes using this finite automata, whether it matches a token or not. And if this lexeme matches a token, then we will tokenize the output. So this will be output. We will get the tokenized output of this lexical analysis phase. Then we have various phases, like here syntax will be checked, here whether the program is semantically correct or not is checked. Here we convert it into intermediate code generation. There are various type of intermediate codes. The 3 address code is the most famous one. Here we optimize the code, and here we convert it into a target code. But the question was asking, in a compiler the module that checks every character of the source text. So here this lexical analyzer checks every character, matches the lexemes with the patterns to generate the tokens. And pattern matching is done using finite state automata. So this is lexical analyzer is the correct answer, as it checks every character. This question belongs to theory of computation subject, and the topic name is context-free grammar. It was asked in GATE 1987. So the question states, a context-free grammar is ambiguous if the grammar contains useless non-terminals, it produces more than one parse tree for some sentence, some production has two non-terminals side by side on the right hand side, none of the above. So what is a grammar? Like even in the English language, we have certain rules which are used to check whether a given sentence is true or not. So same goes with the TOC grammar. So we have certain rules stated down, and we are given a sentence, and we can check whether it belongs to the grammar or not. Sentence, or we can be given a string. So let us suppose we have a string. So what we do is that, let us suppose AAP is the string. We try to derive this string using the rules of the grammar. And there are two trees that we can get in between. We can have a leftmost derivation and rightmost derivation. So suppose we have variable union terminal whole star. So what an LMD states is that we scan the string from left to right and we substitute the first variable that is available using the rules. And what an RMD states is that we have V union T star and we scan the sentence from left to right, right to left, and we substitute the first variable with the corresponding rules. Like we expand using the rules, the right terminal in RMD and the first left variable in the LMD and the first right variable in the RMD. So there are certain rules for a grammar to be ambiguous. We can say that a grammar is ambiguous in just three cases. Let it be a context-free grammar, context-sensitive grammar, it doesn't matter. Any grammar is ambiguous if it has more than one leftmost derivation. Like when we are deriving a string using the rules, we can have more than one leftmost derivation, one tree and two tree, or more than one trees. We have more than one rightmost derivation, or if we have more than one rightmost derivation, then also the grammar is ambiguous. Or if we have more than one parse tree. So these are three conditions for a grammar to be ambiguous. And this is not a condition. If we write a condition, if it has more than one LMD, if it has one LMD and one RMD, then is it an ambiguous grammar? No, we can't say, as the condition need to be made sure on both on LMD, both on RMD, or on parse tree. So let us see the options. So option, this one matches, option B matches. It produces more than one parse tree for some sentence. So if we have more than one parse tree, then the grammar is ambiguous. So option B is correct. This question belongs to theory of computational subject and was asked in GATE 1987. So the question states Fortran is a regular language, context-free language, context-sensitive language, and none of the above. So we need to find to which class this Fortran language belongs. So Fortran language was basically used for scientific computation. So there are two types of error. We all know there are either syntax error or semantic error. They can be logical error too, but let us analyze both these errors. So what a syntax error is, suppose you are writing in C, you are writing int a equals to 5 and you forgot to write a semicolon over here, you forgot. Then it is a syntax error. And what is a semantic error? Suppose you are writing int a equals to, you wrote gate. So this is a semantic error. So what happens during a semantic error? The program will execute, but you will get a wrong output. What happens during a syntax error? Compiler will give you the error. So there are two types of language. First one is like Fortran, so which provides the support for the syntax error but doesn't detect the semantic error. So Fortran is a type of language which allows the semantic errors. And C, C++, or Java, they need to detect both syntax error as well as semantic errors. So the languages which need to detect both syntax and semantic error, they are context sensitive languages. As only using context sensitive language, we can write the rules for checking the semanticness, correctness of the program. And the languages which allow the syntax, which doesn't allow any syntax error, but can't detect the semantic errors, like they allow the semantic errors, they are context-free languages. As we can, using the context-free language, we can just write the rules for checking the syntactically correct program. We cannot check whether a program is semantically correct or not. Thus, Fortran is a context-free language as it checks only syntax error but doesn't check semantic errors. It allows the semantic errors. So Fortran is a context-free language. This question belongs to compiler design subject and the topic name is parsers. It was basically asked in GATE 1987. So the question states a operator precedence parser is a top-down parser, bottom-up parser, backtracking parser, or none of the above. So in compilers, we can say parsing can be of two types. First one is top-down parsing done using top-down parsers, and the second one is bottom-up parsing done using bottom-up parser. So what a top-down parsing is, it basically starts from the root of a tree and then traverses down to all the leaf nodes. So what basically it means is that we will start with the start symbol of the grammar and we'll use the production rules to get only the terminals or the string belonging to the language of the grammar. And in bottom-up parser, we will basically start from the leaves of the tree and will traverse back up using the grammar to get to the root of the tree. So it's basically a bottom-up parser. So here we start with the string or a terminal star and then we trace back to the start symbol of the grammar. This is basically a table that all of you guys should remember so that you can answer these type of questions very simply. So parsers can be a top-down parser or a bottom-up parser. A top-down parser can be with backtracking or without backtracking. Without backtracking, it can be further divided into recursive descent parser or non-recursive descent parser, which is also called an LL1 parser. The bottom-up parsers can be further divided into operator precedence parser or LR parsers. LR parsers are further divided as LR0 parser, SLR1 parser, LALR1 parser, and CLR1 parser. So from this table, you can easily see that operator precedence parser is a type of bottom-up parser. So it's basically operator precedence parser. It's basically a shift-reduced parser, which is basically capable of parsing a subset of LR1 grammars. So the option B is true. This question belongs to data structure subject and the topic name is linked list. It was asked in GATE CSE 1987. So the question states, in a circular linked list organization, insertion of record values involves modification of one pointer, two pointer, multiple pointers, or null pointer. So let me first tell you what is a pointer. So pointer is nothing but it's basically a variable only, which is basically storing the address of another variable. Like let us suppose we have address 1000 over here, this is address 2000, and we have some data over here. Let us suppose we have variable p value. So this variable ptr is called a pointer variable if it is storing the address of another variable, address of p. It's storing 1000, which is address of another variable. So it's called a pointer variable. Now, what is a circular linked list? So for circular linked list, we have structure defined as, we will just have a data. A data can be of any form. Let us suppose integer data, and we will have a pointer s1. We will have a pointer s1. So s1 type, we will have a ptr. So what will happen is, we will have these nodes like this. Each node will have its own address and it will have two parts. So first part will be data and the second part would be address part. Let us suppose the data that is filled over here is 10, 20, 30, 40. Each one has its own address. Let us suppose 1000, 1008, 1016, 1024, and this link is basically storing 1008, this is storing 1016, this is storing 1024, and this is storing null. Now let's suppose we want to let us name this as p, this as q, and let us suppose we want to add a new node over here, node which is called as r and has an address 2000 and has a data 50 and has this as null. So what all pointers do we need to change? So what we need to do, we need to make 1016 point to 2000. So how will we write this in code? We will write, and we also need to make sure that this null points to this 1016. So before changing 1016, what we will do is that before changing 1016, we will make this point to 1016. So with this we will make point to 1016. So we will write this as r's next equals to p next. So r's next will point to 1016, which is p's next. Now we need to make sure that this link gets over and 1016 points to 2000. Here 2000 comes. So what we will do? We will do p's next equals to R. So we have just changed two pointers, this one 1016 to 2000 and null to 1016, first one and second one. So the answer is 2 pointers. This question belongs to operating system subject and the topic name is process synchronization. It was asked in GATE CSE 1987. So the question states a critical region is one which is enclosed by a pair of P and V operations, or here they could have written a pair of down and up operations on semaphores, a program segment that has not been proved bug-free, a program segment that often causes unexpected system crashes, a program segment where shared resources are accessed. So let me explain you this with the help of an example of two programs. Let us suppose we have a program P1 and a program P2. What P1 does? P1 does some tasks and then it does read on a variable A, and then it increments the variable A, and then it writes the variable A. In this shared memory, we have a variable A which is stored in the RAM and has a value, assume it to be 10, and then it does some other things on some variable B, maybe read, decrement, and then write. Then we have P2. What P2 does is that P2 does something, maybe some independent code independent to A, then it again reads A, it decrements A, and then it writes A, and maybe it will do some other task on some other variable G. So now what is a critical section? Here we can see that this part of the code accesses the variable A, and this part of the code of program P2 also accesses the variable A. Here it may be possible that we are running P1 and P2 simultaneously. Let us see what will happen if we will run P1 followed by P2, P1 followed by P2. So P1 will read A to be 10, it will increment A, make it 11, and then write A to be 11 over here. What then if P2 will run after P1, then P2 will read A to be 11, decrement it, make it 10, and then write a 10 over here. So the final result will be 10. Now let us assume concurrent execution, which means P1 and P2 are running simultaneously. So what happens? That is P1 parallel to P2. The output of this was 10. So let us assume P1 reads 10. Now it got terminated. Now P2 comes, it also reads 10. Now P1 comes again, it increments 10 to 11 and then writes A 11 over here. Then P2 decrements 10 and make it 9. It decrements 10 only, not 11, because 10 was already read and it's present in its own local memory. Now it writes A, which is 9 over here. The output over here is 9, which is wrong, as the actual output should be 10. So this is called inconsistency problem. And what is a critical section? Critical section is the section of the code which is accessing these shared resources. So here shared resource is A. So this portion is called critical section, and this portion is called critical section. So critical section is a part of code which is accessing the shared resources. So how can we make sure that this inconsistency do not occur? There are various solutions to this. Like first one is turn variable solution, another one is lock variable solution. There are certain hardware solutions based on interrupts. There is a Peterson solution, and there is a most famous solution called a semaphore solution. In semaphore solution, we are using P and V operations. Like we will, before coming to the code, we will make sure we do P operation, and after exiting we will do the V operation before entering and exit after exiting the critical section. Now let's see the options. So option A states a critical region is one which is enclosed by a pair of P and V operations on semaphore. We can see semaphore is just a possible solution. There are other solutions too. And if semaphore is implemented, then yes, critical section will have P and V operations. But it is not basically the definition of critical section. Because P and V operation is just a part of a solution. It's just a subset of a large possible solutions. It's not necessary that if P and V are there, then critical section will always be there. It's only a part. It's not the correct definition of critical section. Option B, a program segment that has not been proved bug-free. No, it is not related anyway to the definition. A program segment that often causes unexpected system crashes. No, there are no system crashes due to critical section. There is just inconsistency in the data. A program segment where shared resources are accessed. Yeah, it's the correct definition. As here, A is accessed, A is a shared resource. So this program segment where A is accessed is called critical section for both the programs. So option D is correct. This question belongs to compiler design subject and was asked in GATE CSE 1987. So the question states, using long identifiers in a program will necessarily lead to somewhat slower compilation, a program that is easier to understand, an incorrect program, or none of the above. So in a program we can have two things. We can have a keyword or an identifier. So what is a keyword is, let us suppose we are writing loops, then we are using while, we are using for, we may have something if, we may have int. So all these predefined words are called keyword. And what is an identifier? All the variable names that we are using. Suppose we are using college names, CLG underscore name. We are using name. We are using A, B, C. All these are identifiers. Now, let me tell you what this question is asking using long identifiers. So let us suppose we want to store name of the students in a class. So we can store it in string format. We can have either student name stud underscore name. We can either give the variable name stud underscore name equals to, let us suppose Raj is a person in the class. Or there is another option, like we can use a larger identifier name like name of the student underscore in underscore the underscore class, and we can store a student name Raj over here. So both these are correct, both are correct, but it's asking what's the problem if we are using long identifiers. So you will easily understand this by looking at the phases of the compiler. So these are basically the phases of compiler. So what happens is, first we will have our .c file. Let us suppose it's stored in p1.c. Then we give it to compiler. So what compiler does? Compiler converts it into assembly level language. Then we have assembler, then we have linker, then we have loader, and it gets converted into 01 format or executable code. So what a compiler does, it converts the high level language to assembly level language. And compiler has these phases: lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and target code generator. Let us focus on this lexical analyzer. What this lexical analyzer does is that lexical analyzer checks and matches patterns with tokens, matches lexemes with pattern to generate tokens. I will explain you what this means, to generate tokens. So what is a lexeme? Let us suppose we have this code over here. So lexeme is any appropriate word that we are seeing. This string is a lexeme, stud underscore name is a lexeme, equal to is a lexeme, Raj is a lexeme, even this semicolon is a lexeme. So lexical analyzer will scans for the lexemes and will match it with pattern. So what is a pattern? Pattern is predefined thing which is stored, some predefined things, like if anything is starting with colon then it is a string, if this is this then it is a semicolon, if some int is there then it is a keyword. So it matches the lexemes with the patterns, and if anything matches then it generates a token. So we will get tokenized output, like we will have tokens like this for this, and for this we will have, the number of tokens would be same, but just this name of student in the class token will be of different name. We'll have tokens like this, and this is done using finite state automata with outputs like DFA or NFA with output. So what will happen if we are using long identifier? Then when lexical analyzer is searching the string from left to right and is matching the lexemes with the patterns using finite state automata, then here for a long identifier it will take more time to scan and match the finite automata. and hence it will lead to slower compilation. So let's see the options. Using long identifier will necessarily lead to slower compilation, yeah, because lexical analyzer will take more time to scan the lexeme and match with pattern to generate the token. Option B, a program that is easier to understand. No, it's false, because it it may lead to an program that is easier to understand. It doesn't mean, like here stud underscore name is also doing the same thing, and this large name is also doing the same thing. So we can't say that using long identifier will necessarily lead to easier understandable program. It may even lead to more complex program, like here we need to read the entire word and the same significance is provided by this short name student underscore name. So this is false. An incorrect program? No. Both the programs are correct only. Using long identifier do not make the program incorrect. None of the above? No. So the correct answer is option A, somewhat slower compilation. This question belonged to algorithm subject and was asked in GATE CSE 1987, and the topic name is sorting. So the question states, let P be a quicksort program to sort the numbers in ascending order. Let T1 and T2 be the time taken by the program for the inputs 1, 2, 3, 4 and 5, 4, 3, 2, 1. Which of the following holds? So here we need to read this question language very carefully. Make sure that this T1 and T2 are the time, not the asymptotic time complexities. As if it would have been there, then the question answer would have been different. Now let us analyze this for the inputs, like how quicksort will work. So quicksort basically find out a pivot. So what's the time complexity? So what it will do, we can take the pivot from the starting or from the ending, or any random number can also be taken as a pivot. Let us assume pivot is always taken to be the first number. 1 is the pivot. Then what's the output? It will place all the numbers less than 1 on the left side and more than 1 on the right side. No one is less than 1, so nothing will come on the left side, and 2, 3, 4 will come to the right side. Then again the leftmost element I2 will be taken as pivot. Less than 2 nothing, greater than 2 3 and 4. Then 3 will be taken as pivot. Less than 3 nothing, more than 3 4. Now here it will end. So what happened when we are having from 1 to n? Then nothing will come on the left and n minus 1 items will come on the right, and again it will continue. So if Tn is the time complexity of the entire quicksort, and we know partitioning algorithm takes order of n time, as it just makes a one scan through the entire array, and we can assume this n minus 1 time to be t n minus 1. So after solving this, we will get t of n equals to order of n square. And if we are going ahead with the second part, which is 5, 4, 3, 2, 1, then let's analyze this to 5, 4, 3, 2, 1. Here we can take any element as the pivot. Let us assume first item is taken as pivot. Then all the elements less than 5 will be on left and more than 5 will be on right. So 4, 3, 2, 1 will come on left. Not necessarily in this order only, it can be any random order. And nothing is more than 5, so nothing on the right. Then 4 is taken as pivot. Elements less than 4 on the left, which means 3, 2, 1 on the left, nothing on the right. Then 3 is taken as pivot. Elements less than 3 on the left, which is 2 and 1 on the left, nothing on the right. Then 2 is taken as pivot. Elements less than 2, which means 1 on the left and nothing on the right. So here what happened, if we have items from n to 1, then first all the n minus 1 items will come on the left and nothing will go on the right. So if Tn is the time complexity of entire quicksort, then order of n time for partitioning and T of n minus 1 for solving this n minus 1 length subproblem. The time complexity comes out to be order of n square. We can easily see that both are order of n square only. So if the question was about the asymptotic time complexity, if T1 and T2 represented asymptotic time complexity, then option A was true. But here you can easily see T1 and T2 are the actual time taken, the time taken in the seconds. So here the answer would be, let us suppose it's for 4 elements. So what's the complexity? Order of n square. Let us assume it to be order of 4 square into some constant. Constant will always be there. So order of 16c. And what happens for this? Here it's 4 length and here it's 5 length. Although it is also n square, but it will be order of 5 square c. So it will be order of 25c. So this 4 element will take less time than this 5 element. So option C will be true over here. If it was asymptotic complexity, then option A was true. As it is normal time taken, thus option C is true. This question belongs to programming subject and was asked in GATE CSE 1987. So the question states, study the following program written in a block structured language. What will be the output of the right statements marked 1 and 2 in the program if the variables are statically scoped? So we are using static scoping. Option A 36, option B 67, option C 37, option D none of the above. So it's not basically any standard language like C, C++ or Java. It's basically a dummy language, block structured language, but we can easily understand it. So let me explain this code to you. So this is the main function. Between begin and end, there is always main. This is procedure Q, function Q. This is function P, and these are global X and Y. So first main will be executed. So it will do x equals to 7, y equals to 8. So do main has its x and y? No, it do not have. So which x and y will it change? It will go to the global space and change its x and y. X it will make it to 7, y it will make it to 8. Now it will call q. So main will call q. Q has two variables x and y. So q has its own x and y. It will do x equals to 3, y equals to 4. As q has its own x and y, so it will do q equals to 3, y equals to 4. Then it will do p of y, which means it will call p with a value y. Does q has y? Yeah, it has 4, so it will call with p of 4. Now we will come to procedure p. Here we will do n. This p has a variable n, which will take n equals to 4 from this function q. 4 will come over here and get stored in this integer n. Now it will do x equals to n plus 2 divided by n minus 3, which means 4 plus 2 6 divided by 4 minus 3 1. So x equals to 6. But it do not have any p. So here the scope problem arises. So scope problem can be solved by two methods. We can have a static scoping or we can have a dynamic scoping. So in static scoping, what happens is that if we are having a scope problem, which means a variable is not present in a function or a code, then we will check the outer nested structures. And in dynamic scoping, we will check according to the function call stack. So basically, while running the program, we are maintaining a stack in which we are pushing the function names, and then if a code do not have a variable, then it checks in its lower call stack functions whether it is present or not. So here in static scoping, we are checking the outer nested structures. So here p do not have x, so it checks in the outer nested structure, which is global x and y. So what it does x equals to 6. So it does x equals to 6 in this outer structure, outer global x. Now p will end, it will come back to q. What q will do? Q will do write of x. Does q has x? Yeah, it has its x. So write will write on the console, it will write x value, which is 3. Now it will do return back to main. What main will do? Main will do write of x. Does main has x? No. So it will check the outer structure. Outer structure is this global ones for main 2. So it will write x means write x of global, which is 6. So the answer is 3 and 6. Option A. This question belongs to programming subject and was asked in GATE CSE 1987. So the question states, study the following program written in block structured language. A program has been given. It's not a standard language, but it's a dummy language. We can easily understand the code. What will be printed by the right statements marked 1 and 2? What will be the output of these statements 1 and 2? If the program if the variables are dynamically scoped, which means all the variables are using dynamic scoping. Option A 36, option B 67, option C 37, option D none of the above. So what's a scope problem? Let us suppose we are in a particular code and we do not find a particular variable but we have accessed it, then scope problem arises. It can be solved either by static scoping or by dynamic scoping. So what a static scoping is, if we are having a scope problem, then we will check in the outer nested structures. So according to the nesting we will go, and in dynamic scoping we will check the function call stack. So what happens is that we are in the RAM, we are having a stack which is called function call stack. Whenever we are calling a function, we are writing its name over here like f1, f2, f3, and let us suppose we are currently executing f4 and this scope problem arises. Then we will look for the variable in the call stack from top to bottom. If this variable is present in f3, we will update it over there. If it's not there, we will check in f2. If it is present in f2, then we will use f2 and do not check in f1. So in the closest one that we will found, we will use read or update that one only. It's called function call stack. So let us solve this problem by using dynamic scoping using the function call stack. So this is our main function, this is our Q function, this is our P function, and these are global variables x and y. So first main will be called. So what will happen? We will have our stack, main will be pushed over here. Then it will do x equals to 7, y equals to 8. Does main have x and y? No. Scope problem arises. If scope problem arises in the main, if we do not have anything below it, then we will update the global ones. So we have global variables x and y. We will update x to be 7 and y to be 8. In main, if there is a scope problem, we will always update the global ones. Now it will call the Q. So Q will be pushed in the call stack. We will call the Q. When we come to the Q, it has own variables x and y. So it has local variables x and y having garbage value initially. Then it will do x equals to 3 and y equals to 4 in the local variables only. Then it will call P of y. P of y. Why does it have local y? Yeah. It will call with P of 4. And we will put P in the call stack. Then what we will do? We will check what all variables do P have. P just have an n local integer which will get this value 4. So n equals to 4. Now P will calculate x equals to n plus 2, which means 4 plus 2 6 divided by 4 minus 3 1. So x equals to 6. Does P have any x? No. So how will it check? Now scope problem will arise. So it will check the function call stack. P do not have, so it will ask Q whether Q has x or not. Yes, Q has this x and its value is 3. So what P will do? P will update that x to 6. So it will update this 3 to 6. Now it will come back to Q. While coming back, it will pop from the stack. Now it will come back from, now Q will write x. Does Q has x? Yes, Q has x and its value is 6. So in the console, we will print 6, which is local for Q. Now it will pop back from the stack and will come to main. Now what main will do? Again write x. Does main has x? No, main do not have any x. X is not present over here. So it will check in the global variables. X is 7. So it will print 7 and then main will also be popped and stack would be empty and our program will end. So what all was printed in the console? Console means the output screen that we are seeing. So we will get output 6 and 7. So option B is correct. This question belonged to engineering mathematics subject and the topic name is linear equation. It was asked in GATE CSE 1987. So the question states, if A, B and C are constants, which of the following is a linear inequality? Ax plus bcy equals to 0, ax square plus cy square equals to 21, abx plus a square y equals greater than equal to 15, and xy plus ax is greater than equal to 20. So let me first decode for you what's a linear equation. So linear equation has two terms, linear and inequality. So what a linear means, like we will have these variables, like x and y are variables. So linear means that all the variables will have will have at most degree 1. At most degree 1. Which means it can have 0 degree or it can have 1 degree. Which means either we can have just x or nothing. We can't have x square, we can't have x cube. We will just have x or nothing. What is inequality means? Equality is this equals to. So inequality means equal to is not allowed. Then what else is allowed? Not equal to is allowed. Greater than is allowed. Less than is allowed. Greater than equal to is allowed. Less than equal to is allowed. So let us see the options. Here equality is there. So it's not a linear inequality. So this option is false. It's linear as here x and y just have degree 1. It's linear but it's not an inequality. It's an equality. Here x has degree 2 and y has degree 2. So it's not linear, it's quadratic. And even it's not inequality, it's equality. Here a b x, here x has degree 1, it's fine. Here a square, but it's a constant, y has degree 1, yeah, this is an inequality. So it is a linear inequality. Here let's see, x and y both are variables. So it's quadratic, not linear. X square is not there, y square is not there, even two variables product shouldn't be there. It will become quadratic, it's not linear. It's inequality but it's not linear, so it is also false. So option C is correct. This question belongs to engineering mathematics subject and the topic name is polynomials. It was asked in GATE CSE 1987. So the question states the equation 7x to the power 7 plus 14x to the power 6 plus 12x to the power 4 plus 3x to the power 4 plus 12x cubed plus 10x square plus 5x plus 7 equals to 0 has all complex roots, at least one real root, 4 pair of imaginary roots, none of the above. So what is an imaginary root? Whenever we are having under root of -1, it's basically an imaginary number and we write it as iota. And any root of the form a plus iota b, it's an imaginary root, and any other root which just have a value a, it's a real root. There are basically two observations that we need to remember for answering this question. If there is a root, if an equation E1 has a complex root C1 a plus iota b, which means when we write C1 in place of x, we will satisfy this equation. Then C2, which is a minus iota b, will always be also a solution to this equation. It will also be a root, which means all the imaginary roots come in pair. Or we have even number of imaginary roots. So number of imaginary roots can be 0, 2, 4, 6, 8 and so on of the form 2 to the power n, where n belongs to natural number. And what are the number of roots possible? For any variable, what's the highest degree is equals to the number of roots possible. Number of roots, they can be real or as well as imaginary, equals to highest degree. What's the highest degree? So what's the highest degree over here? Highest degree is x to the power 7, which means 7. So number of roots equals to 7 and it includes both real and imaginary roots. Now let us see all the options one by one. All are complex roots. So what are the number of roots? We have just now verified that the number of roots are 7. If all of them need to be complex roots, then the number of complex roots should be even, but 7 is not an even number. Thus option A is false. Option B, at least one real root. Now let us see all the options. Can we have 0 complex root? Yes. Then number of real roots would be 7. Can we have 2 complex roots? Yes. Then the number of real roots would be 7 minus 2, 5. Can we have 4 complex roots? Yes. Then the number of real roots would be 7 minus 4, 3. Can we have 6 complex roots? Yes. Then the number of real roots would be 7 minus 6, 1. Can we have 8 complex roots? No, because 8 is greater than 7 and maximum roots possible are 7. Thus we can easily see number of real roots will be always greater than 1. So we will always have at least one real root. Option C, 4 pair of imaginary roots. As imaginary root come in pair, so 4 pair means 8 imaginary roots. Can we have 8 imaginary roots? No, it's not possible as the maximum number of roots possible are 7. None of the above. No, it's also not an answer. So the answer is option D, at least one real root. This question belongs to engineering mathematics and the topic name is linear algebra. It was asked in GATE 1987 CSE paper. So the question states a square matrix is singular whenever the rows are linearly independent, the columns are linearly independent, the rows are linearly dependent, none of the above. So what's a square matrix? A square matrix is any matrix in which number of rows and number of columns are equal. If we have 3 rows, then we have 3 columns, or we can say basically an n cross n matrix is called a square matrix. What is a singular matrix? A matrix is singular if its determinant is 0. Now let's see what this term linearly dependent and linearly independent means. Let us take an example of a matrix with 3 rows and 3 columns, a 3 cross 3 matrix. It's a square matrix. Let us take its values to be 2, 5, 6 and over here to be 4, 1, 5 and this one to be -2, 4 and 5. So linearly dependent means if we can write any of the row or any of the column as a linear combination of the other rows or columns. Like here, this one is row 1, row 2 and row 3. We can see that row 1 equals to row 2 minus row 3. 2 minus 4 minus 2. 5 minus 4 1. 6 minus 5 1. So here if we will apply the elementary operations, then we can apply this operation like R1 equals to R1 minus R2 minus R3. Then R1 can be made as 0. And if we can make all the rows or all the columns 0, then determinant will be 0. Thus, if we have a matrix and we have linear dependency, then its row or column will be 0, can be made 0, and thus its determinant will be 0. And if we have determinant 0, then it's called a singular matrix. Thus, a singular matrix will have a linear dependency. All rows are linearly independent? No. The columns are linearly independent? No. We must have a linear dependency. The rows are linearly dependent? Yes. So the option is C. It's the correct. This question belongs to engineering mathematics subject from the topic polynomials and was asked in GATE 1987. So the question states, if fxi into fxi plus 1 is less than 0, then option A, there must be a root of fx between xi and xi plus 1. There need not be a root of fx between xi and xi plus 1. The fourth derivative of fx with respect to x vanishes at xi. The fourth derivative of fx with respect to x vanishes at xi plus 1. So first let us analyze this statement. When product of two numbers is less than 0, here we have fxi into fxi plus 1 is less than 0. If both of them are positive, like we have plus 3 into plus 4, it's plus 12, it will be greater than 0. So this won't occur. When we have both negative, like minus 3 into minus 4, it will be plus 12. Less than 0 won't occur. If we have one as negative, like minus 3 into 4, if we have first one as negative and the second one as positive, then this will occur. Or either if we have first one as positive and second one as negative, then also the product would be negative, which means either the first one or the second one needs to be negative. Now let us try to draw it on the number line. Let us suppose we will draw both the cases on the number line. This will be x, this will be fx, this will be fx, and this one would be x. Let us assume the points, this one to be I and this one to be I plus 1. So first case is fxi is positive and fxi plus 1 is negative. And the second case is this is I plus 1, fxi is negative and fxi plus 1 is positive. So how will we draw the slope? So here it was previous GATE question. It was asked in 1980s, and there we can assume the function to be continuous. There can be two cases: either the function can be continuous or the function can be discontinuous. But here at that time mostly continuous functions were assumed. So we will assume a continuous function. If we have a continuous function, then definitely it will meet the x-axis at some point. Let us mark it as C.
And in this case also, it will meet the x-axis at some point. Let us assume this one to be C2 and this one to be C1. And at this point, f of C1 will be 0. And over here, f of C2 would be 0. Thus, when we will do f of C2 equal to 0, which means C2 is a root. And C2 will lie between I and I plus 1. And C1 will also lie between I and I plus 1. So the option, there must be a root of fx between xi and xi plus 1. It's true. There need not be a root, it's false. The fourth derivative of fx with respect to x vanishes at xi. Fourth derivative has no relation with this question. But if assume that here it was given that the function is discontinuous, then what can happen? If the function is discontinuous, then what can happen is that then we can have it something like this. Like I plus 1. It can be positive, the second one could be negative, and it can be a discontinuous function, which means there is a possibility that there is no root between I and I plus 1 in both the cases. In the second case also, it can happen. Like we can have xi as negative, xi plus 1 as positive, and it is possible that it is discontinuous, so there is no root. But it was if it was given discontinuous. As nothing is given, we will assume it to be continuous, and the answer would be there must be a root of fx between xi and xi plus 1. Option A.